Hi, good evening. My name is Mohak Chadha. I'm a final year PhD candidate at the Technical University of Munich, and this is my WoSC 2023 presentation on the topic GreenCourier carbon-aware scheduling for serverless functions. A bit about who we are. We are the chair of computer architecture and parallel systems at the Technical University of Munich. We work in a wide variety of domains such as high performance computing, cloud computing, quantum computing, and edge computing. So if you're interested in any of these areas, feel free to reach out to us. Looking back at the brief history of the cloud, from bare metal servers to infrastructure as a service, platform as a service, and then more recently to serverless computing, aka function as a service, in which users are only responsible for implementing fine-grained pieces of code called functions and deploying them onto a function as a service platform, while all responsibilities around infrastructure management are automatically handled by the cloud provider. Some prominent examples of commercial function as service platforms include AWS Lambda, Google Cloud Functions, Azure Functions, and IBM Cloud Functions. Typically, these cloud providers see around 1.1 billion function invocations each day. If we look at some of the challenges in sustainable serverless computing, one of the challenge is that due to the significant level of abstraction provided by the fast computing model, the core new technologies that enable it consume significantly more amount of energy as compared to conventional technologies. For instance, Firecracker, which is a lightweight micro VM used in production in AWS Lambda and AWS Fargate, consumes 19 joule of energy per function invocation request. Another challenge is that the geographical region or data center for serverless function execution is pre-selected during function deployment in all commercial fast offerings. As a result, the varying carbon intensities, that is grams of CO2 emitted per kilowatt hour of energy produced for the different geographical regions, is not considered for function execution. To address these challenges, we implement and present GreenCourier, a scheduling framework that intelligently schedules serverless functions across geographically distributed Kubernetes clusters to minimize carbon emissions for function execution at runtime. It builds on Kubernetes and Knative, which is an open source function as service platform used in production in Google Cloud Functions and Google Cloud Run. GreenCourier consists of three main entities: users, the central control plane, and the geographically distributed independent provider clusters. For connecting the independent provider clusters to the management cluster, we use the open source project called Lico, which internally utilizes Virtual Kubelet. Virtual Kubelet cloaks a provider cluster as a virtual node and connects it to the management cluster. Using our framework is significantly uncomplicated. In the first step, users implement functions in different programming languages such as Go, Python, Node.js, or Java, changes the scheduler name in the YAML specification file, and deploys them onto our management cluster. Following this, our custom scoring plugin for Kubernetes, implemented using the Kubernetes Scheduler API, scores the different geographically distributed provider clusters depending upon the region's current carbon efficiency. To obtain carbon-related information about the different geographical regions, we implemented a metric server that currently supports two marginal operating emission rate sources of the local electricity grid, that is watt time, and the carbon-aware SDK. Our metric server is modular and can be easily extended to support other sources such as electricity maps. The metric server exposes a REST API that can be utilized by a scheduling plugin. After obtaining the carbon efficiency scores, our scheduler assigns the function pod to the geographically located cluster with the highest current carbon score or efficiency. Finally, after completion of the binding cycle, the function can be invoked by the user. Moving on to some results, we tested our framework on Google Kubernetes Engine with Knative for multiple geographically distributed clusters spread across Europe. We used several serverless functions performing different tasks such as DNN inferencing and LU decomposition. For emulating actual user behavior, we used production open source Azure function traces for generating requests. And we compared our strategy with two other approaches. the default scheduling strategy in Kubernetes, and a geo-aware scheduling strategy that maximizes the placement of functions in regions which are closest to the management control plane. For evaluation, we use the following metrics: carbon emissions, function response times, scheduling latency, and binding latency. The last two metrics are Kubernetes specific. Scheduling latency represents the time between the node assigned event generated by the Kubernetes scheduler and the pod creation event generated by the replica set controller. Binding latency represents the time between the node assigned event and the pod running event generated by Lico kubelet. Now, to quantify and estimate carbon emissions on invocation of a serverless function, we used the software carbon intensity specification developed by the Green Software Foundation. The SCR for an application is given by the shown equation. E represents the energy consumed by the application. I represents the geographical location-based marginal carbon intensity. M represents the embodied carbon emissions for the hardware where the application is executing. R represents the function unit of application, for instance, the number of requests per second. For more info about the SCI, you can check the follow QR code. Moving on to some experimental results. With our strategy across all serverless functions and for a single function invocation, we observed 8.7% average reductions in carbon emissions as compared to the default scheduling strategy, and 17.8% average reductions as compared to the geo-aware scheduling strategy. But there are also some trade-offs. As compared to the default scheduling strategy, we observed 10.26% geometric mean average slowdown in response times and 16.24% geometric mean average slowdown with respect to the geo-aware strategy. The major reason for the bad performance with respect to the geo-aware strategy is that the most carbon efficient regions in our experimental setup, that is Spain and France, are farthest away from our management cluster in Frankfurt, leading to higher response times. If we look at the scheduling latency, we observe our GreenCourier scheduler takes 539 milliseconds on average for scoring and assigning carbon efficient nodes to pods as compared to 550 milliseconds taken by the default Kubernetes scheduler. If we look at the binding latency, we observe an average pod binding latency of 8.28 seconds with GreenCourier and Lico as compared to 4.53 seconds per pod with kubelet. So there are two reasons for this. First, due to the resource abstraction added by VK, and additional synchronization is required in GreenCourier for communicating state information between the management cluster and the provider clusters. Second, frequent communication across geographically distributed clusters via public internet, increasing the binding latency. In contrast, all communication in the traditional setup is done within a virtual private cloud. In the future, we plan to extend the management control plane of our framework to make it highly available and disaggregated. We also plan to look at Lico to improve the function response times by enhancing the network address translation scheme and decrease the binding latency by improving the status synchronization of offloaded pods. Thank you for your attention.